Good morning. My name is Raihan Yusuf Rifansyah, and I'm from Universitas Pendidikan Indonesia. And today, I will present our research titled Comparative Study of Machine Learning Models for Inverse Kinematic Prediction of a Flexible Tube Bridge Mechanism in Robotic Charging Station. Robotic charging systems are critical in enabling autonomous docking and electric vehicle charging. For successful operation, they require precise alignment to ensure efficient power transfer and mechanical coupling. At the heart of these systems lies the wrist mechanism, a component that manages the docking interface. By introducing a flexible tube, we enhance compliance, absorb misalignments, and reduce wear during docking. However, this flexibility comes with a challenge. The tube allows passive deflection in 6 degrees of freedom, three translational, and 3 rotational. This complicates the inverse kinematic process, making the traditional inverse kinematic methods insufficient for accurately predicting joint angles in flexible systems. To address this challenge, we propose using machine learning to predict the inverse kinematic of the wrist mechanism. Machine learning models excel in capturing complex, nonlinear relationships, outperforming traditional methods in such scenarios. Additionally, finite element method analysis provides insight into the static deflection behavior of the flexible tube under various forces, offering valuable physics-based understanding of the system. The primary objective of this study is to evaluate the accuracy of different machine learning models, including a hybrid approach combining machine learning with physics-based insight. The risk mechanism over 3 controlled degrees of freedom, mainly yaw theta1, pitch theta2, and roll theta3, to control the orientation of the end-effector. The flexible tube introduced passive deflection in 6 DOF, including translation, dx, dy, and dz, and rotation, rx, ry, and rz. This deflection occurred during docking and must be accounted for the inverse kinematic predictions. To understand the system motion, we consider both forward kinematics and inverse kinematics. Forward kinematics involves calculating the end-effector position and orientation in 3D space using transformation matrices for yaw, pitch, roll, and deflection. Inverse kinematics determines the joint angles theta1, theta2, and theta3 required to achieve specific end-effector position xn, yn, and zn, accounting for the passive deflection introduced by the flexible tube. To train and evaluate machine learning models, synthetic data was generated to simulate the wrist mechanism operation. The end-effector motion was modeled using sinusoidal parametric mode function to represent movement in 3D space, with position determined by amplitude and frequency. Deflection modeling accounts for translational and rotational deflection using similar parametric equation, simulating the tube response to external force. Dataset inputs included an effector position xn, yn, zn, and deflection, while output were joint angles theta1, 2, and 3. The dataset was split 80% for training and 20% for testing, capturing the diverse configuration to ensure robust mean model evaluation. The models evaluated were feed-forward neural network, recurrent neural network, long short-term memory, random forest, extreme gradient boosting, late gradient boosting, Gaussian process, and hybrid method. While uh, while the finite element method analysis was not directly used in machine learning training, it provided key insight into the flexible tube static deflection behavior. This helped refine the understanding of the system dynamics and the interaction of forces. The models were evaluated based on root mean square error. Physics-based method and the hybrid model achieve perfect accuracy. You can see here is the physics results. The line fitted perfectly to the actual line. And here's the MLP. It does not fit perfectly. Instead, it's squiggly, achieving RMSE of just 2.51. Here is the RNN, which the roll is not good enough, but the yaw and pitch good, achieving RMSE of 0.44. The LSTM is quite good here, achieving RMSE of 0.32. Random forest is not very good, achieving RMSE of 1.03, while XGBoost is fitted nicely at RMSE of just 0.11. LightGBM, LightGBM performance are in the middle of 0.27. Support factor machine achieve RMSE of 0.31, while GP achieve RMSE of 0.32. And you can look at the hybrid model. It's basically the same as the physics method, achieving RMSE of 0.00, which is near perfect. Among the machine learning models, LSTM excelled in handling time series dependencies, with RMSE just 0.32. LightGBM show robust performance with the RMSE of 0.27. Other models like MLP, Random Forest, and XGBoost had higher errors, indicating challenges in capturing system dynamics. In conclusion, this study then demonstrated that the hybrid model achieved the best performance with an RMSE of 0.00, combining the strengths of machine learning and physics-based approaches. Among machine learning-only models, LSTM and LightGBM were the most effective with RMSE of 0.32 and 0.27 respectively. Models like MLP struggled with the system complexity, highlighting the importance of model selection. For future work, we aim to optimize the LSTM, XGBoost, LightGBM, and hybrid models to enhance their predictive capabilities, conduct experimental testing to validate these models in real-world scenarios, implement real-time prediction with adaptive feedback control to improve docking precision and system responsiveness. That's all that I can say right now. Thank you for your attention. I look forward to discuss with your thoughts and answering any question about this study. Thank you.